So now we're going to continue on the land-based drawdown theme with Professor Justin Borevitz from the Research School of Biology at the ANU.
Thank you very much, Aurora. Thanks, Michael Jeffries, for introducing the topic. Also, Aurora and Elke Rolling in the audience and I came up with this proposal over the last few months, and we presented it to the ANU Grand Challenges. And so I'm going to rehash that here and also add a few more points that really speak to the specific science underlying what Michael Jeffries introduced. So carbon drawdown is certainly one of the major goals and the topic of this conference. And land-based sequestration is a wonderful opportunity. It also addresses the resilience in agriculture and the habitat disruption theme that underlies our ecosystems and protecting biodiversity. So I'll try to address those three topics today. It's really a triple threat that we're facing. There's more and more being asked of our agriculture lands to produce not only food, but animal feed and fuel. So we have room to lean down and decrease the land. We also are struggling to maintain production given the soil degradation and limited water supplies. And on top of that is more extreme weather. So the old contrast between biodiversity, we've expanded our agricultural footprint into habitat. So they're preserving the rich carbon stocks, especially tropical forests that are at threat of agricultural expansion. So expansion is not really a solution because we're going to disrupt more of the important ecosystems. Now, climate change we've talked about. We're already in overshoot. We need to draw down atmospheric carbon as fast as possible. And we need to do that on less cropland. And we heard yesterday about bioenergy and how that's actually an additional demand on land. And it's almost at the scale of all of our agricultural production. So how are we going to address this triple threat? This is the drought ongoing in Australia, and the dark red is the lowest on record. This is a new update from yesterday's Bureau of Meteorology. The last 18 months, so much of New South Wales and Queensland are in record droughts, and this is going to become the new normal for the next decade and continuing to become more extreme. We've seen a lot of land clearing, and this is the drawdown that we're talking about, the negative emissions. There's a huge amount of shift in the normal business as usual, so this is the avoided emissions, and this is the drawdown on top of that that's additional. And one of the things I wanted to point out is that it's the land sector that has some of the largest uncertainties and the largest interannual variability. And rather than sort of being thrown around with the more extreme climate to come, I think that if we get in and really manage this land sector, we have an opportunity to do what's done on those best years and try to avoid some of the losses. So this is the cycle, the intensifying cycle of droughts, fires, and floods, and that's washing away the soil carbon, the soil fertility. We've got our land use is actually also often going in the wrong direction. So the state of the globe is essentially that we're managing half of it is in the agriculture space, and that's increasing. So protecting the existing forests and shrublands is really important, but that's in addition to increasing the productivity of agricultural lands. And most of that is rangelands, almost all of the Americas together, 4 billion hectares of rangelands. And on the edges of the cropland and the rangeland is really 1 or 2 billion hectares of marginal land. And that's the challenge for regenerative agriculture, and that's the opportunity. And also most of our protein and calories is coming from the cropland. So this is the opportunity for regenerative agriculture. Not sure why that happened. Okay, 1 second here. Oh, we're fighting each other there. All right. Great. So what is the solution? So the solution is to try to overlap the food production area with the carbon sequestration area and the biodiversity habitat. So this is how we solve the land use paradox. There's not enough land in the world to do everything. We can't continue to expand for bioenergy at the expense of food production, at the expense of biodiversity. So we need to really go vertical, rebuild the soils, as we've just heard, rebuild the canopies, and then our agriculture in between. So multi-layers. And what we need is both an investment in land improvement, and much of Australian land has sort of just been actually degraded or unimproved, and with, you know, high resolution planning tools, we can figure out exactly how to restore the catchments, restore the water, insert renewable energy, and monitoring systems so that we can have precision technology at scale. And then the management tools are going to be the plants and the microbes for carbon capture, and biochar and rock dust for storage. And the way this works is we'll need a few early adopters and innovators to get this off the ground with experiments and designs. Then we need to build, monitor, and ultimately manage and learn, and this cycle can be repeated out across the landscape. So we'll be looking at space and time, multispectral approaches, both satellite, top-down, and bottom-up with ground-based sensors and modeling. And we'd like to put this into a predictive framework where we can make prescriptions about how to best build and then manage these landscapes. And that's what I'll take you through today. The core of the concept is that even though we're emitting 10 or 12 gigatons of fossil carbon into the atmosphere, that's really dwarfed by the size of the biosphere. The land system is drawing down 100 or more gigatons in photosynthesis, and that's finally balanced with the release of both plant respiration and soil respiration. And so to enhance the Earth system, we'd like to increase photosynthesis by providing this limiting nutrients and water, and decrease the respiration by capturing some of the biomass that would normally degrade and be released, charring it and returning that on the ground into the soil, and also using the activity of the soils to capture some of the soil carbon in carbonates and enhance rock weathering system. So together, along with limiting emissions from both agriculture and fossil fuels, we'll be able to get to this negative emissions state. So that's the potential. What can we do in Australia? So we do have a lot of land. This is more than 300 million hectares in agricultural system, and I've selected here the croplands, which is about 30 million hectares, and the pasture lands, another 30 million hectares, and about 40 million hectares of scattered trees. There's also known as rangelands as targets for regeneration. And we think we can draw down, on average in good years, 10 tons of carbon CO2 per hectare, depending on how much rainfall really. And so this could be a gigaton. Underneath each one of those pixels is a farm unit. It's 100 hectares, 1 square kilometer, and we need the contours, as we heard from Michael Jeffries, to break through the clay layer and allow the water to infiltrate. So this is re-engineering the catchments with heavy equipment. And then also those will become the tree lines so that roots can quickly get in and bring the carbon down into the soil. We have a renewable energy based pump hydro system to catch the water on the farm and move it up to the hillside for irrigation. So this is the infrastructure. And the core is essentially using renewable energy to maximize the water use efficiency and nutrient use efficiency so that the rain percolates into the ground or into our dams that can be retrieved with demand response irrigation to get us through the extreme droughts. And so most of the water then is up through transpiration rather than evaporation. And this cycle then can drive the carbon cycle for increased plant growth that we then capture to bring carbon into the soil, improving the minerals, the pH, making phosphate more available to increase soil growth, plant growth, and accelerate this carbon cycle. So we can model this at the individual tree and at the individual farm forest unit. So we're trying to balance the above ground agricultural system, find the right mixture of crops, pastures, and trees that shouldn't be really monocultures of crops, pasture, or trees, that we need to integrate a few animals with our crops and trees in the right place so we can have canopy cover and hold the soil. Those above ground layers then feed the below ground layers, which improve the above ground layers. And you get agricultural productivity and sales off the top while you invest in the fertility below ground. And this allows you to play some of the counter-cyclical cycles and the weather extremes. So what do we have going so far at the National Arboretum? My lab's developed this phenomic and environmental sensor array where there's a grid of weather stations and cameras that can look both at real-time growth of the trees and identify some genetic outliers here, as well as the environmental signal shaping both growth and phenology. The scale is such that we can go from the Earth satellite level down to the forest plots with towers on cameras, so that towers so that we can get really precision response, identify diseases early, identify plants that are growing that are highly adapted and maybe doing better than the group, so that we can select them. We can look at annual growth rates. This is the drones flying over that then create a three-dimensional map. All of this can be incorporated into models so that we can look in virtual reality, if you will, at what the potential for new farms could be, what the growth rate would be on the ground. And I think the Emissions Trading Fund folks would be very happy to see the actual trees and their heights with precision. We can see into the ground with soil moisture, and this allows farmers to really learn and manage precisely their environments. To scale this up, we want to collaborate with new technology companies that are rapidly deploying reforestation approaches so that we can put the exact right seed in the right place at the right time, maybe after a fire and a flood, drop the seeds in so they can get established and we can get to scale quickly. This is biocarbon engineering, and ultimately we think we can model for any location, any potential farmer that wants to adopt these approaches, what their farm would look like in 10 years. And then it can be financed and we can invest in our landscapes. So let me go to the next slide, please. On ground, we have the solutions of plant diversity with biochar for capture, rock mineral fertilization, and microbes. And these four pieces of the puzzle then interact to regenerate the landscape and ultimately produce food and fiber. Now, the biophysical models that I've explained, we're getting more and more precision there and ability to extrapolate, interpolate into the future, into more challenging climates. We also need to incorporate the economic and social models, and this is actually the work that Aurora and others on the team are working from. So together we have a lot of new information coming in about the exact genetic basis of the different trees and trying to pre-select adaptive genotypes to grow in new environments, and the real challenge is to expand this out into new environments. And so we've gone recently to sample the entire species-wide diversity of eucalypts, and these are now in the lab. We're ready to start planting these next generation seed orchards to really maintain and enhance the diversity. And this is a little drone shot from what would be the top of a Eucalyptus regnans overlooking the seed orchard in Adelaide. So these trees have the potential to get to hundreds of meters in hundreds of years. Here's an interpolation of what the right genetic basis would be across the environmental range. This is the boxgum grassy woodlands, where we've made projections about what is the right thing to plant in the right environment. And these are model-based approaches of how fast trees can regenerate once you provide them with fertilizer and agriculture, fertilizer and irrigation. So we really can jumpstart this approach. This is one concept of a farm forest that we'd like to develop. So I'll just finish up now with some of my own back-of-the-envelope modeling. As we just look at business as usual, the climate's getting worse, and more farms are both losing carbon and money. But with bailouts, we may slow the rate of economic loss, but we're still going to lose on the ecological front. But with regenerative agriculture, where we invest in the infrastructure of the land, we hope to be able to recover and repay, and many of the farms will come into both a positive economic and environmental outlook. And that's, a simple 30-year model with extreme climate change and variability coming that we can see. So these experimental systems, we heard Michael Jeffries suggest that we need to really get to reinvest in our agricultural trial sites. I think that's on our agenda as well. We really need to plug in the data and the sensing and the modeling capacity to existing experimental lands, and from that we'll be able to make more and more accurate projections. The next stage is really to engage with some large farms. Actually, of the 100,000 farmers, it's probably 20% of them that are producing 80% of the yields. And so engaging with some of the big farmers to shift the tide to regenerative agriculture is on the next horizon. And ultimately then we want to do this at a catchment or watershed level and transition the agroecosystems. And I think that would become the tipping point that can get us to this 100 million hectares that will deliver for the climate. At 100 million hectares, 10 tons per hectare is a gigaton, which is about 10% of the world's national demand. So Australia can really lead in this approach. And the unique thing about the proposal with regenerative agriculture is it's engaging the landowners and the farmers. Rather than being a top-down policy from Parliament, it's really a bottom-up approach from farmers. And we don't need to wait for carbon pricing or handouts. I think that can all help and accelerate this, and so coupling a national policy with a groundswell from the farm sector is a real opportunity. And I just want to finish with the rock dust. As we're thinking about transitioning, a just transition for coal miners, where does the rock dust come from? One of the, along the east coast here is these basalt provinces, which have some phosphate, but also a lot of calcium and magnesium that can bring up the pH and as well sequester carbon. So we heard about enhanced rock weathering yesterday, that you need about 5 tons of rock to neutralize 1 ton of coal. So it happens to be that these are in the same locations where our major investments in mining already exist, especially here in Newcastle. There's a lot of equipment pulling out coal that could be shifted right to basalt mining for regenerative agriculture. So we can see a new rebirth in our farm sector and a rebirth in our mining sector that are both moving to regeneration rather than extraction. And the equipment is already here. The landscape geoengineers are just working in the wrong direction, and we'd like to model at least how to reverse that process. Thank you very much.